Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams, Associate Professor Emeritus of Electrical Engineering, and I am your genial host and raconteur for this presentation, which we're entitling Wrong Place. There we go. Bonus Circuits, Part 3, applying the Beams operational amplifier technique to frequency-selective op-amp circuits involving one capacitor. A brief recap of the BOAAT method. It's a simple method for analyzing all sorts of op-amp circuits. An op-amp circuit which consists of an op-amp, an input voltage source, an output voltage, and two linear networks. This is a common topology for many applications. Network A produces a voltage at the non-inverting input as a weighted combination of input voltage and output voltage. And network B produces an output voltage, which I've labeled V sub n here, at the inverting input as a linear combination of the input voltage and the output voltage. And we invoke the virtual ground criterion that the voltage V sub P at the non-inverting input and the voltage V sub N at the inverting input will be equal to each other. And from that, we derive the final BOAAT expression. V out to V in is A1 minus V1 over B2 minus A2. And it has an amazing range of applications. And we've already looked in a previous video of that. Looked at applications involving DC circuits using resistive linear networks. Now let's look at networks involving a capacitor. Here we have an inverting integrator. A1 and A2 are both 0. B1 is determined by this RC voltage divider with the capacitor as the lower branch of the divider and the resistor is the upper branch, V out forced to 0 while V in is applied. B2 is determined by applying a voltage to the output while V in is set to 0. And now we have the same RC network, but now the capacitor is the upper branch and the resistor is the lower branch of the voltage divider. And putting these coefficients into the BOAAT formula gives us V out to V in is minus 1 over S C sub F R sub I. Now, okay, I'm using the Laplace transform here. The S is the Laplace transform variable, and it's just natural for me to think in terms of the Laplace transform. If you haven't had the Laplace transform, though, don't despair. If you know the phasor transform, you can substitute J omega from the phasor transform for S from the Laplace transform, and the results of this transfer function can be expressed in the phasor domain. So in the phasor domain, the transfer relationship is minus 1 over J omega C sub F R sub I. The relationship here is that of an integrator. If you're familiar with the Laplace transform, you know that multiplication by 1 over S in the Laplace domain is the representation in the time domain, that's the Laplace transform of integration in the time domain. This circuit implements an output voltage in the time domain. VO of t is minus 1 over RI C sub F times the integral from 0 to t of Vn of tau d tau, where tau is a dummy variable of integration. And of course, if there were an initial condition at the output voltage of VO of time t equals 0, we could add that to the formula. Let's take a look at another circuit, an inverting amplifier with a low-pass frequency response. Here, A1 and A2 are both 0. B1 determined by forcing V out to 0 while applying V in. You can see there's an RC voltage divider with RF and C sub F as the lower branch and R sub I as the upper branch. When I go to measure or determine B2, I force a voltage at VO while V in is held at 0. We have the same RC network, except now R sub I is the lower branch and RF parallel with C sub F is the upper branch. And the transfer relationship that comes from the BOAAT formula is minus RF over RI times the quantity SCFRI plus 1. This computed transfer function is that of a low-pass frequency response inverting amplifier. It has a DC gain of minus RF over RI, which we determined by setting S equals 0. And it also has a minus 3 dB frequency or break frequency of 1 over C sub F R sub F radians per second. This is an expected and known result. So let's try something a little more complicated. Here's a circuit that, well, let's just see what it does, okay? A1 is determined by setting VO to 0, which in this case doesn't matter because there's no connection from V sub P back to VO, but we then apply an input voltage and determine V sub P, and it is determined from V in by this RC voltage divider network with C sub X as the lower branch and R sub X as the upper branch. A2 is 0. And I've made these two resistors RI1 and RI2 equal in value, so that makes coefficients B1 both 1/2. And when we apply, or we use these as inputs to the BOAAT formula, we get V out to V in is, here's just a direct substitution, and here's after a little bit of manipulation, a little bit of normalization, 1 minus SCXRX over 1 plus SCXRX. Now, this gizmo has a DC gain of 1. Let S go to 0, and you get 1 over 1. The high frequency gain, if you let S become J omega and let omega run off to infinity, you get minus 1, or a gain of 1 with a phase shift of 180 degrees. Interesting. As a matter of fact, at any frequency, the magnitude of V out to VI or V in is constant because the magnitude of the numerator is always the same as the magnitude of the denominator at any frequency, but the phase is not constant. The phase of the numerator is opposite that of the denominator, and they are frequency dependent. So this is what we call an all-pass network. Constant magnitude response, but a shifting phase with respect to frequency. This circuit, by the way, is available to you as bonus circuit number 8. Now let's take a look at the frequency response of the simulation of bonus circuit number 8. You can see the magnitude response from 10 hertz to 100 kilohertz is flat at 0 decibels, and the phase response begins at 0 degrees and passes through minus 90 degrees at 1 kilohertz with the values in the circuit and approaches an asymptotic limit of minus 180 degrees at high frequencies. So the simulation shows that this network does exactly what we were expecting. Phase shifting while maintaining a constant magnitude response. So we've seen an application of the BOAAT technique to frequency selective circuits involving one capacitor. We'll conclude this series of presentations on the BOAAT technique with application to frequency selective circuits involving 2 capacitors. That will be the concluding presentation in this series. For now, I appreciate your time, and it's been my privilege to be your presenter in this video, and we will look for you again soon in the concluding video of this series.